In this chapter, we're going to begin our discussion of bending in beams. And this follows two previous chapters where we first dealt with axial loading. You remember in axial loading, we have a part that is long and slender, typically with a constant cross section, and it has a load along that axis. So if it's a tensile load, it will increase in length. If it's compressive, it will decrease in length. And we solve for the stress and deflection with axially loaded parts. That was followed by a chapter on torsion. And with torsion, we also had typically circular cross sections, long and slender, but instead of an axial load, we now had a torque or moment about the x-axis, which caused torsion, which led to shear stress in our member, as well as a total twist. So now we're going to continue this with bending of beams. Now, the idea with bending of beams is in order for something to be a beam, it has to, again, be long and slender, meaning maybe 10 times longer than any of your dimensions perpendicular to that length. Long and slender, it needs to have a constant cross section. And what makes it a beam and not an axially loaded member is it needs to have loads perpendicular to that cross section with what are called transverse or perpendicular loads. We typically draw this in 2 dimensions as something that is long and slender with a constant cross section. And by transverse or perpendicular, I mean a load in the y direction, given that our beam is lined with the x direction. So a downward force F, that's considered a transverse load. That wouldn't be the only thing on the beam, right? It might have some kind of supports on either end, and it could have a distributed load. But the point is with a beam, it's got loads that are perpendicular to the x-axis. Common supports. The 2 most common are simply supported. And that is where we have a long beam, has a pin on one end and a roller on the other end. Pin plus a roller. The other very common beam support we have is called a cantilevered beam, is one that is fixed on one end and free on the other. So fixed and free. These are our 2 most common types of supports, but we can have other variations. Most of the other variations are what we call statically indeterminate. And a statically indeterminate beam is very easy to make. You simply start with a statically determinate beam. Statically determinate means we can solve for all of the reactions using our equilibrium equations from statics. To make it statically indeterminate, all we need to do is add another support, like a roller right there. You add additional supports beyond the ones that we can solve for using statics alone, it becomes statically indeterminate. Beams have internal shear forces, which we're going to use the letter V for shear force like we have earlier in the semester, and they have bending moments. And we're going to use a capital M to represent the bending moment. And the idea is that if you'll remember from our axial loads and our torsion, oftentimes the axial load would be very constant for a very long length of a member. Torque inside of the structure could be constant everywhere along here in the middle. Well, with beams, typically the shear force V and the bending moment M vary with the x location along the beam. What we're going to be doing in today's class is figuring out how big is the shear force and the bending moment at different places along the beam. So our goal today is to sketch how V and M vary. We're going to call these shear force and bending moment diagrams. And the goal of this is typically to find out where are they biggest and how big are they, because the shear force and bending moment, whatever its maximum value is likely to determine when we're going to have failure. So this is a key thing for designing beams. So ultimately, we want to find V max and M max, our maximum shear force and our maximum bending moment along that beam, and sketching out how these quantities vary as we go from left to right across the beam will enable us to figure that out. Let's do a cantilever beam here for illustration purposes and apply a force P at the end. This cantilever beam altogether has a length L. We can go and draw a free body diagram and we can solve for the reaction forces back here at the wall. Free body diagram of the whole thing. It's always a good idea to do this before you start cutting things open. Make sure you know all of your external reaction forces. If I have a force P there at the end, I'm going to have, call this maybe point A, I'm going to have a Y component of force, I'm going to have an X component of force, and I can potentially have a couple moment MA. If I use my equilibrium equations next, I can sum forces in the X direction, and I find out that AX is 0 because there are no other forces in the X direction. If I sum forces in the Y direction, those have got to equal 0. If up is positive, I get AY minus P equals 0. So AY is equal to P. And if I sum the moments about point A equal to 0, counterclockwise is positive, I get MA minus P times the total length is 0. And so my couple moment at A would be P times the length. Now that we have those external reaction forces, we can start cutting open our beam to find out how big is the force at different points along the beam. Let's go cut it right in the middle. And we'll draw a free body diagram of half of the beam. And as you remember with internal loads, we can draw either everything to the left of the cut or everything to the right of the cut. On the right half of the cut, I've got P, and then the internal loads at that cut. On the left half, I will have P upward, that was my AY, and I would have a bending moment, MA, which is equal to PL. At the cut, in general, we're going to have 3 potential unknowns for a 2-dimensional problem. We will have a normal force, we'll have a shear force, which our positive sign convention for shear is going to be down on that surface and up on this surface. The other thing we're going to have in here is an internal bending moment, and we tend to draw that positive this way. So these are the internal loads that are happening. Now, our distance here is L over 2. You can use either of these diagrams now to solve for the shear force and solve for the bending moment. Here, I'm going to sum forces in the Y direction equals 0, P minus V equals 0. So my shear force is equal to P. If I did the same thing on the other diagram, summing force in the Y direction equals 0, we would have V minus P equals 0. So we again get V equals P. So if sum moments out the cut equals 0, and I pick counterclockwise as positive, I have my internal bending moment M that I'm trying to solve for. These other forces don't contribute. Now going the other direction, I've got P times this distance away, L over 2. So I'm going to have minus P times L over 2. And then finally, also in a positive direction, I've got plus PL. That M is minus PL over 2. And if I do this same thing on the other side, if I sum moments about the cut, N and V don't cause any kind of moment. P does, and it will be clockwise. So I'll have minus P, and the distance away is L over 2, and then also minus M. Bring M to the other side, and I get that M is minus PL over 2. Same thing that I got before. I just found the internal shear force and bending moment at one point along the beam. We need to find it now at all the other points along the beam. So what I'm going to do, instead of cutting it in the middle like I did, I'm going to do a different cut. I'm going to cut it right here. I'm going to cut it at a position that I'm just going to label X. And X can take on values from 0 to L. And let's get an equation to express what V is going to look like. So we're doing the purple free body diagram, where I have P downward, I have V upward, potentially have an N, and I have a moment that I need to solve for. I totally forgot to sum forces in the X, but you guys probably already know the answer to that. If I sum forces in the X, the only X force I have here is my normal force. So you get that the normal force is 0. From the X forces, N equals 0. If you sum forces in the Y direction, you get that V equals P. So summing moments about the cut, I'm going to have minus M minus P times how far away it is. So I need to figure out this distance. And I called the distance from the left end to the cut X, and the whole length was L. So this is L minus X. So I'll multiply P times L minus X equals 0. And I solve for M. M is equal to minus P times L minus X. So now we've got an equation that tells us how our moment's going to vary with position. So what we like to do now for today, we're going to draw what are called shear and moment diagrams. We're just going to plot what we just found. So I like to draw the beam with whatever's on it, on my picture. And now straight below it with the exact same width, I like to draw my shear force diagram. And then directly under that, my bending moment diagram. What we found is that the shear force is always equal to P. And it has a constant value the entire width of the beam. And for some reason, we like to shade these in. So there's our shear force diagram. The shear force in this beam is P everywhere. I like to find the endpoints. It looks to me like this is the equation of a straight line. So if I plug in x equals 0, I find the moment at x equals 0 is minus PL. So let's come down, call this minus PL. Makes sense that a moment should have units of force times length. And then at the other end, when I plug in x equals L right here, I'm going to get moment is 0. So this needs to be a straight line that goes from minus P over L to 0. And now I should be able to draw a straight line from one of those to the other. And then if we were concerned about designing this beam, we would want to say that the max V is equal to P, and the max moment is equal to, in magnitude, is equal to PL. We typically do these in magnitudes, and this occurs at the fixed support. So we would expect that if this beam was going to break, it would break right here at this wall, because that is where the bending moment is the biggest. Complete example with real numbers. So for my example, I have a simply supported beam. It's pinned on the left end, and it has a roller on the right end. We'll call the left end A, the right end B, and this has got a uniform distributed load over the entire length. That distributed load has a magnitude of 3 kilonewtons per meter, and the beam has a width of 4 meters. And we are going to say X starts on the left and goes right. And we're going to try to get an equation to express how the shear force and bending moment change with X, and then we're going to plot it. So find V as a function of X, we're going to find M as a function of X, and then we are going to draw the shear force and bending moment diagrams. All right, I've told you before, almost every problem in this class starts with a free body diagram, and this is no exception. I like to first draw the free body diagram with everything still attached. All we're doing is removing the supports. So at A, we have a pin. That means I'll have an AY and an AX. At B, we have a roller, so I only have a BY. And then I'm going to draw my distributed load on here by finding the equivalent force and putting it at the equivalent location. So you'll recall that means I need to find the area under this curve, which is 3 kilonewtons per meter times 4 meters. And I'm going to put it at the centroid of that rectangle, which is right in the middle of the beam. So this magnitude of this force is going to be my 3 kilonewtons per meter times the 4 meters that it acts over, which is 12 kilonewtons. Next, you would use equilibrium equations, but I'm going to do this kind of quickly. AX comes out to be 0 if you sum forces in the X direction. And AY and BY are both going to be equal to each other and equal to 6 kilonewtons. You can find that by summing moments about A or B to find one of them, and then summing forces in the Y direction to find the other. We're going to go back to our original picture, and we're going to go over this arbitrary distance X, and we're going to cut the beam open. So we're going to do another free body diagram based on the cut at X. I'm going to keep everything to the left. You can keep everything to the right if you would prefer. So I just have this little piece of the beam. Acting on it are AX, which is 0, so I'm not going to bother drawing that, and AY, which is 6 kilonewtons upward. I also have some distributed load acting over this little piece, but I only want to keep the amount of distributed load that acts over my little piece that I'm drawing. I do not want to include the distributed load that acts on the other part of the beam. So I'm going to need to calculate again how big this distributed load is. So it's going to be 3 kilonewtons per meter times, guess how far over it acts? X. Remember, the length of this thing is X. Okay, so where's the location of that going to be? The location of this force is going to be at X over 2. Now, on the cut open face, I would need to draw my shear force, normal force, and bending moment using my positive sign convention, which looks just like that. If we sum forces in the X, we get that the normal force is 0. It will be for most of these problems. We sum forces in the Y direction. Pick a sign convention. It looks like I have 6 kilonewtons upward minus 3 kilonewtons per meter times X minus V. If you want to call this V of X and M of X, you totally can. It's a function of X equals 0. Now we can rearrange that and we get that V of X, 6 kilonewtons minus 3 kilonewtons per meter times X, or more simply 6 minus 3X. That looks like the equation of a straight line. But let's also sum moments about the cut to solve for our bending moment. So for summing moments about the cut, I will have, first of all, I'll have M of X. And then also in a counterclockwise direction, I'm going to have 3 kilonewtons per meter times X. That's the magnitude of the force. And now the distance away from the cut would be X over 2. So times X over 2. And then finally in the other direction, I've got a minus 6 kilonewtons, and that distance away is X equals 0. M of X equals 6 kilonewtons times X minus 3 kilonewtons per meter times X squared over 2. Or more simply, M of X is just 6X minus 3X squared over 2. And if anybody is saying, hold on, that V of X and that M of X equation sure look like they might be related by a nice calculus thing called the derivative. If I take this M of X equation, I take the derivative, I get the V of X equation. If you notice that, you would be absolutely right. We're going to use that in just a minute as a shortcut for drawing these. So let's go ahead and draw out what the shear force and bending moment diagram will look like for this beam. I'll start by drawing the beam one more time. And it's got a uniform distributed load. We had a 6 kilonewtons there and 6 kilonewtons there. And this is a 3 kilonewton per meter distributed load. Now straight underneath it, I'm going to draw my shear force diagram. And then underneath that, we're going to draw our bending moment diagram. And again, it's really helpful to kind of just look at what will the endpoints be and maybe what shape will it have. So that V was, I'm going to plot V equals 6 minus 3X. So if I plug in X equals 0, the V will be up at 6. 6 kilonewtons. On the other end, what happens when X is at the far end? This whole thing was 4 meters wide. So when you plug in X equals 4 meters, you get 6 minus 12. So we're going to end up exactly down at minus 6 kilonewtons at the other end. So that will be our other point. Go between the two and draw a straight line. And we usually bring it back up to 0 at the end and shade it in. So that is my shear force diagram for this beam. It is a straight line with a slope of minus 3. Minus 3 happens to match the 3 right there. I've got a load that's going downward, going on downward with the same slope as that magnitude. And did you notice on the left, we start up 6, and on the left end of the beam, we have an upward force of 6. And then on the right end, we ended up at -6. So to get back to 0, we had to go up 6, which should match our reaction force of up 6 on the right end. Finally, we need to plot our bending moment diagram. I like to plug in endpoints again. If you plug in X equals 0, you get moment is 0. So this is going to start out at 0. And if you plug in X equals 4, this first term will give you 24. And the second term would give you 16 divided by 2 is 8 times 3 is 24. You get 0 again. So this bending moment is going to start and end at 0. And that is a parabola. If you want to find out like the middle point, it might be helpful to plug in x equals 2. I have a moment right here with a magnitude of 6 kilonewton meters, because if you plug in x equals 2, you get 12 minus 6 is 6. So the highest point is 6 kilonewton meters, and it's a parabola. So we're just going to sketch it in as a nice little parabola. And the important thing is that the maximum moment, M max, has a magnitude of 6 kilonewton meters. So V max, that's going to be 6 kilonewtons. And this one occurs at the middle, and this one occurs at the ends. Now, if any of you remember from calculus when you were doing things like velocity and acceleration curves, and you notice velocity and acceleration are, one is the derivative of the other, one's the integral of the other, you might start to notice some patterns here. We had a constant distributed load, so our V curve has a constant slope. Here we have a slope that is decreasing, which means that this one is concave down. Here we have a positive V, which means that our M has a positive slope. When our V is equal to 0, that is when the slope of our moment diagram is equal to 0. Now we've got a negative V, which means that our M needs to be decreasing, and this is gradually getting to be bigger, which means that the slope is getting bigger and bigger and bigger as we go down. So we had a constant distributed load that led to a linear V with a quadratic M. So we're going to put all that together and use what's called the graphical method. So the graphical method takes advantage of the fact that the derivative of that shear force diagram is equal to, we're going to actually technically call it minus W of X. The reason that happens is because somebody somewhere decided that if distributed load was downward, we should call that positive. What the equation means in words is the slope of the V curve is equal to the distributed load curve. Like we had with that previous problem, right? The magnitude of it was 3. It was going in this direction. And so that means that this has to have a downhill slope of exactly 3. Let me even draw it on here. That slope is minus 3 kilonewtons per meter, which matches the 3 kilonewtons per meter right here. If the distributed load is pushing down, then the shear diagram has to be going downhill. We also have a relationship between our moment curve. The slope of our moment is equal to V. What that's saying is that the slope of the M curve is equal to the magnitude of the shear force at that point in time. So when our shear force was big and positive 6, this had a big positive 6 slope. When our shear force went to a zero magnitude, this had a 0 slope. And when our shear force went to minus 6, this had a downhill steep negative 6. If I'm looking at 2 different points along the curve, if I find the change in the V, so let's say I'm going from here to here, and I want to find how much does V change going from point A to point B. This is going to come from integrating, technically there's a minus here, W of X dx between points 1 and 2. What that means is that the change in the V curve between any 2 points is equal to the area under the W of X curve. So let me show you how that works. If I'm going from here to the middle of the beam, and I want to know how much does the shear force drop from here to here, take and integrate and find the area underneath this curve. Happens to be 3 kilonewtons per meter times 2 meters, which is 6, and I go from 6 down to 0 because I had 6 under this curve. Continuing on from here to here, area under this part of the curve is also 6 kilonewtons, so I'm going to drop another 6 kilonewtons going from here to the end. I can do that with M as well. If I want to know how much the moment increases from there to the middle of the beam, I can find that by simply taking the area under this curve. Area under this curve is 1/2. The base is 6 kilonewtons. The height is 2 meters. So 6 kilonewtons times 2 meters is 12 kilonewton meters divided by 2, you get 6. So from here to here, that height change has got to be 6 kilonewton meters because that was what the area of this curve was. M2 minus M1, I simply take the area under the V of X curve. So that means the change in M between any 2 points is equal to the area under that M of X curve. Another example. I have got a shaft, treat it like it's simply supported. And this is being loaded up by 2 forces. I have an 800 Newton force, and then farther over, I have a 1500 Newton force. I've got 125 millimeters from A to the first force, and then I have 600 millimeters to the next force, and finally 75 millimeters to point B. And before we do any shear and bending moment diagrams, we want to do a free body diagram to find our reactions. So for my simply supported beam, I'm going to have a BY, AY, AX is going to equal 0 because there are no X forces. Downwards, I have 800 newtons and 1500 newtons. So let's use some equilibrium equations. If I sum the moments about point A, I'll get BY times, looks like it's 800 millimeters away. Then I got minus 800 newtons, which is 125 millimeters from point A, minus 1500 newtons, which is 725 millimeters away from point A. So we solve, and we get BY equals 1484 newtons. And then from summing forces in the Y direction, we will find that AY has got to be 816 newtons. We know all our forces now. So what I want to do now is sketch my shear force and bending moment diagram. So I'm going to draw them directly under my free body diagram. Like that. Here's V and here's M. So whenever you have a point force, that is going to cause your shear force diagram to have a step change. So at the very beginning of the beam, we start off with an upward 816 newtons. So I'm going to start my shear force diagram up here at 816 newtons. Next, equations up here that we had said that the slope of the shear curve is equal to however big the distributed loading is. We don't have any distributed loading. So no distributed loading means a 0 for W. So the slope of V will also have to be 0. So that means it just is a horizontal line. Then I meet my 800 Newton downward force. You remember how when we had an upward force, we jumped up? We got a downward force, we're going to jump down by exactly 800. So I was at 816. I'm going to jump down 800. So now I'm at 16 newtons. And now what happens? I have no distributed load. So I have a slope of 0 until we reach our 1500 Newton force. Then we got to jump down by 1500 newtons, which I think is going to cause us to land at approximately minus 1484 newtons. And then that, again, we have no distributed loads, we have no slope. And then when I get to the end, I have an upward BY. BY was exactly 1484 newtons, so it brings me back up to 0. That's always a great double check that you've done everything right, is your final reaction force should take you back up to 0. And there is my shear force diagram. I'm going to color this in with 3 different colors, and you'll see why in a minute. So there's a green one. Let's make this middle part blue and make this last one pink. And if anybody needs to know, my V max, you can then find out, is actually 1484 newtons. That is the absolute max shear force anywhere in this beam. It occurs in that last section right here. And isn't that interesting that for this beam, even though there is a 1500 Newton force on it, the shear force inside the actual beam is never any bigger than 1484 newtons. Moving on, let's do the bending moment next. Bending moment, I do not have any moment applied here because it is a pin. So that means that my bending moment needs to start at 0. The only time your bending moment will start at something other than 0 is if you have a fixed support or an applied couple moment right there. But if you don't, it just starts at 0. Okay, and then what we said next was the slope of the M curve is equal to however big your V curve is. So if the V is 816, that means positive 816. That means that the slope of this diagram is going to be 816. because it's got to match the 816 up here. Now, how about if we want to find out how high that's going to end up? By finding the area under the V curve, right? Remember what our equation said? Our equation said the slope of M is equal to V, and the change in M is equal to the area. Oh, I wrote that wrong. It's equal to the area under the V curve. So we can find that. So I'm going to call this area 1. Area 1 is equal to 816 newtons times 125 millimeters. I'm going to call that 0.125 meters. And I get 101.9 Newton meters. So my magnitude right there is 101.9 Newton meters. And I found it simply by taking the area of that green section. Okay, then what happens next? Now I drop down to still a positive slope, but a much smaller positive slope. So for the next section, I need to draw this with a much shallower, smaller positive slope. How big should that slope be? That slope should be 16, because this guy is 16 right there. So slope is 16. And if I want to find out where it lands, what I need to do is to find the difference in M from the one point to the next. I need to find the blue area. So area 2, call this guy area 2. That's going to be the height, 16 newtons, times the length, which is 600 millimeters or 0.6 meters. That comes out to be 9.375 Newton meters. Add that to what we had before, and that means that my max moment right here turns out that it's going to be 111.3 Newton meters. That's at that peak right here. Now, I find this really helpful to go ahead and calculate area 3. Area 3 should be, technically it's negative 1484 newtons, and the length that acts over is 0.075 meters. And if you calculate that, that should come out to be 111.3 Newton meters, meaning that we should go right back down to 0 at the end. Should come back to 0. And the slope of this section should be a negative 1484 is the slope of that one. So steepest slope of all. And if anybody asks, where is the maximum moment, M max? Well, the value of it is that 111.3 Newton meters. And it occurs right under that 1500 Newton force. So if you were concerned about this beam breaking, that is where it would break. All right, and we solved this problem. We found, without actually taking any cuts and without having to draw little free body diagrams and a ton of equilibrium equations, we simply used graphical methods. And to recap what we do there, when you have a point force, that means you need to jump in the same direction as the point force by the same magnitude. So here we went up by AY, down 800, then down another 1500, and then that left us back up to 1484 at the end. First, to figure out the slopes, we start with a steep positive slope, we drop to a shallow positive slope, then we have a steep negative slope. To figure out how big these height differences were, we used the area under this curve, tells you how much of a change in moment you have between the first point and the second point. The area number 2 tells us how big of a change of moment we have between the second point and the third point. And that third area tells us how big the moment has to change from that third point to the end of the beam. And that's a negative jump because it's a negative area. I want to do one more example. Call this guy example 3. We have a beam. It's pinned on the left at A, and it has a roller on the right at B. It has applied to it a downward 3 kilonewton point force, and then it has applied to it a clockwise 450 Newton meter couple. And finally, it has another downward 3 kilonewton force. I'll put some dimensions on here. This first section is 300 millimeters. The second one is 200 millimeters. The third is 200 millimeters. And the fourth is 300 millimeters. And we're asked to draw the VM diagrams and find Vmax and Mmax. When we're asked for Vmax and Mmax, we care about the absolute value. I'm going to start with a free body diagram. I'll have an AY that I need to solve for. AX is going to come out to be 0. I will also need to solve for BY. Downward, we have 3 kilonewtons. We have another 3 kilonewtons. And then this is what's going to make this problem harder than the last one. I have a 450 Newton meter couple. And couples always make things harder, don't they? So equilibrium will help me find AY and BY. I'm going to sum moments about point A. And in doing that, BY is, I think that adds up to 1,000 millimeters away from point A. So that's the moment caused by BY. It will be counterclockwise. Clockwise, I'll have minus 3 kilonewtons times that one is 700 millimeters away. And the other one, minus 3 kilonewtons, is only 300 millimeters away from point A. And then finally, also clockwise, I have my 450 Newton meters. Oh, everything else I just wrote down was kilonewton millimeters. Well, guess what? A kilonewton millimeter and a Newton meter are the same thing. That all equals 0. So we can solve that, and we get BY is 3.45 kilonewtons. Now we can sum forces in the y direction. And we get that AY needs to be 2.55 kilonewtons for this to work out. Now we need to draw our shear force and bending moment diagrams. We're going to do these as quickly as we can. I'm going to draw them directly under my free body diagram. Just helps me line up what's happening on the free body diagram with what's happening on the moment diagram and the shear diagram. So we got V and M. Let's do the shear diagram first. So the first thing that happens on this as we work our way left to right, always go left to right along your beam. First thing that happens is we encounter an upward force of AY. So initially our diagram needs to jump up to a value of 2.55 kilonewtons. We have no distributed load from here to here, so we need to have a slope of 0. Next, we have to drop down 3 kilonewtons. So when dropping down 3 kilonewtons, I'll cross 0 and I'll end up at a minus 0.45 kilonewtons. Then again, I have no slope, so we're going to stay constant. And here's a trick. Couples do not impact shear force at all. Just like when we're summing forces, we don't include couples at all. We just include forces when we're summing forces. We also don't pay attention to those couples when we're doing the shear force diagram. They will not affect it at all. So we keep going right on past that couple moment like it doesn't exist. And then we're going to go down another 3 kilonewtons. So we're at minus 3.45 kilonewtons. And then your double check you've done everything right is at the end of the beam, we go straight back up and BY was equal to 3.45 kilonewtons. So that should always work out that way if you've done your equilibrium equations correctly and then you've drawn your shear force diagram correctly. You should come back to 0 at the end. So somebody wanted to know what's Vmax. Vmax happens to be equal to 3.45 kilonewtons, which is in that far right section of the beam, right here between the 3 kilonewtons and the end. So for my bending moment, we start at 0 because we have no couple here at the end, no couple. So we start at 0. And we're going to start with a positive slope of 2.55. So we're going to start by going uphill with a slope of 2.55. So where are we going to end up? Oh, I can figure that out by finding area 1. Area 1 equals, it's just a rectangle, so it's 2.55 kilonewtons. And the length that that acts over is 300 millimeters. And if I multiply kilonewtons times millimeters, I end up getting Newton meters. If I multiply those out, I get 765 kilonewton millimeters, which is also equal to Newton meters. So our max value here is going to be 765. That's at the end of the orange rectangle. Now what's going to happen is our slope changes from positive to negative, but fairly shallow. So I'm going to go negative fairly shallow, but I'm not going to keep going forever because what's going to happen is I'm going to encounter this 450 couple. And the 450 couple, I want you to think of it as being a jump in your moment diagram. So we were coming along. I'm actually going to break this guy up. Let's break up this into two pieces. So maybe I'll color one of them a different color. We'll leave one of them green. And let me make the other one pink. So we're coming down along the green curve with my slope of minus 0.45 as my slope. And how far down would I have come? I need that green area. We'll call that area 2. And that's got a magnitude of minus 0.45 kilonewtons. It gets multiplied by 200 millimeters. I calculated that as minus 90 kilonewton millimeters or newton meters. So we're just dropping 90. So we were at 765. We dropped 90. So now we should be at 675. So our height right here is 675. We were at 765. We've dropped a little. Now we have a point couple. And that couple, because it is clockwise, is going to make this jump upward by 450. So this jump needs to be exactly 450. I was at 675, so I add 450 to that, and I end up at 1125 Newton meters or kilonewton millimeters. And now I'm going to go downhill again with following the pink curve, that same minus 0.45 slope. So my area, my pink area, call it area 3. Well, that's going to be exactly equal to area 2, minus 90 kilonewton millimeters or newton meters. So I was at 1125. I take away 90 and I end up at 1035. Okay, finally, I have my blue curve right here. So I'm going to find the area of that, call that one area 4. Okay, area 4, let's find it. It's got a magnitude of minus 3.45 kilonewtons, and it lasts for 300 millimeters. So if we multiply that out, we get minus 1035 kilonewton millimeters or newton meters, which is great because I happen to be sitting right at 1035. So this will take me right perfectly back to 0. And the slope there should be pretty big and negative. The slope should be a minus 3.45 slope. Moment max, hey, that's going to be that 1125, call it newton meters. It occurs right there underneath the couple. Occurs where that couple acts. And that's the end of the shear force and moment diagram example. To kind of recap what we did that was new here, we had an applied couple. This couple shows up right here in our equilibrium equations. So it influences how big BY and AY are equal to. If this couple weren't on here, BY and AY would both be 3 kilonewtons, but the couple is shifting loads a little bit more over onto this end. So that's why BY ends up being bigger than AY. The couple itself, though, other than those changes in how big BY and AY are, it doesn't actually have any impact on our shear force diagram because it's not a force, it's a couple, it's a moment. But when we go to draw our moment diagram, that point couple, we treat it kind of like a point load where a clockwise couple is going to cause our moment diagram to jump upward, just like an upward force caused our shear force diagram to jump upward, and a downward one caused a downward jump in that diagram. Otherwise, we're grabbing the slopes of these, slope of that one from the orange curve, slope of that one slightly negative from the green, slope of that one slightly negative from the pink, and slope of that one big and negative from the blue. And then we found all of these intermediate values of how high is the moment going between these 2 points by finding the 4 areas, area 1, 2, 3, and 4. And that concludes today's lesson on shear force and bending moment diagrams.